For the chapter objectives, students should be able to explain and discuss the heat treatment, hardenability, and annealing process for metal alloys, as well as other types of material processing, which we are going to look at afterwards. Meanwhile, for lesson objectives, at the end of the semester, students should be able to analyze the physical properties of engineering materials and concept of corrosion and metal alloys microstructure, phase diagram, and heat treatment processes. As for the topic content, these are the things that we are going to learn for today. Number one is heat treatment, which includes hardenability, annealing, normalizing, tempering, aus-tempering, and mar-tempering, which we are going to look at on what are the processes involved and its effects towards microstructure. Number two, we are going to look at on the mechanical properties, whereby different properties, a different structure or phases which produce will have different mechanical properties. Well, as mentioned to you in previous lecture, materials can be divided into two, which is ferrous alloy and non-ferrous alloy. Ferrous alloy or ferrous metals are actually metals that contain iron and steel. Meanwhile, non-ferrous metals refer to those metals that do not have iron or that do not have iron components in it. And for heat treatment is actually a process of heating the metal without letting it reach its molten condition or melting stage, and then cooling the metal in a controlled way to select desired mechanical properties. Heat treatment is used to make either make a metal stronger or more malleable, more resistant to abrasion, or more ductile. So if you look at the concept for heat treating the ferrous alloys, is that number one, to force a metal to do something, the normal laws of solubility will not let to do it. Number two, usual case is to cause one phase to dissolve in another when it normally will not. So we must have a two-phase region with a single phase region at a high temperature. When we heat up to higher temperature, the metal becomes one phase. Then when we cool fast enough or at a faster rate, we retain the high temperature phase at lower temperature, and where it may exist as that phase or change or transform into something else that is very useful to the design or to the final product. Before we proceed with this topic on the heat treatment, these are the terminology that you should remember and you should understand. By right, in previous lecture, this terminology is already explained to you or already exposed to you, like what are the plain carbon steel. Plain carbon steel exists between 0.03 to 1.2 carbon, which is at this area, and the location of ferrite, this is the location for alpha ferrite, this one is for austenite, and this one is for cementite. Other than that, you should also remember the reactions that occur in iron carbon phase diagram, which includes peritectic reaction, eutectic reaction, as well as eutectoid reaction. And if you notice from our previous lecture, eutectoid steel equals to 0.8% of carbon, and if the percentage of carbon is less than 0.8%, then it is called as hypoeutectoid steel, and meanwhile more than that, it is known as hypereutectoid steel. And again, a revision from previous lecture. Once the metal, the iron carbon, the steel being slowly cooled from austenite temperature, which is austenite temperature, then slowly cooled to temperature 750 degrees C, then it will change from austenite into 100% perlite. And this is the microstructure for perlite. And for hypoeutectoid, which is before a eutectoid point here, this one, slowly cool the temperature, slowly cool the steel, we change the microstructure into alpha ferrite and perlite. And then moving to hypereutectoid, which is the percentage of carbon equals to 1.2%, for example. By right, it has to be more than 0.8% of carbon. That is called as hypereutectoid. And for example, the materials being heated up until austenite temperature, which is equals to 950 degrees C for this case, and then start to cooling down, slowly cool, forming eutectoid cementite and perlite, this one. And okay, so for today, we are going to look at on the transformation as well as undercooling for these phases. For example, before this, in previous lecture, you have learned that slow cooling will will form different structure of the materials. For example, slowly cool the metal from austenite phase will form alpha ferrite and cementite. However, this transformation can be changed by varying the temperature for cooling. It's either rapid cooling or hot cooling. So, for example, we use the iron carbon steel phase diagram or system, whereby we use C not equal to 0.76 weight% of carbon. If you notice here, the cooling temperature reaching 675 degrees C and maintain at that temperature, this one. So initially it will form 0% of perlite when it touch this green line, and then after certain time it will form 50% of perlite in it once it reach this dotted line over here or curve, and then longer time will produce 100% perlite when it reach this this red curved line over there. So basically, we can control we can control the transformation of the microstructure of that steel. Other than slow cooling or control cooling, we can there's also we can also do a what we call it as a rapid cool in salt bath to a desired temperature. For example, this one. Firstly, we heat the steel until the temperature, until it reach austenite temperature, which is above 273 degrees C. Then the steel being placed in salt bath for isothermal transformation, they call it, at some temperature, which is the temperature has to be below austenite temperature. Then after that, hold it for a certain duration and moving it to cold water quench at room temperature. So this is called as isothermal decomposition of austenite. For example, let's look at what happened to the microstructure when we use isothermal decomposition. So this case, from austenite temperature, heating it to austenite temperature, then start to cool it using salt bath at the temperature below than austenite temperature, which is equal to 705 degrees C for this case. After certain duration, we will start to see a coarse perlite forming in that steel. Then after 76 minutes, the microstructure change to cost per light. Meanwhile, if you look at this, we call it, this graph is the a graph for austenite transformation or phase transformation. S curve, this is S curve. S curve next to axis indicate the time necessary for isothermal transformation for austenite to begin. Okay, and the second curve, this is the second curve, indicate the time required for transformation to be completed. The phases exist. The phases exist in this graph is cost per light. This is cost per light. This one is a fund per light, and this is the area for binite, and the bottom part over here is martensite phase. So this one is the cooling cooling point, which is temperature below than austenite temperature. Okay, so following this line, then you should be able to produce different types of structure which is needed. And this one may only occur for carbon steel equals to 0.8 weight%. Okay, so isothermal transformation of eutectoid steels at temperature 727 and about 550 produced per light microstructure. Okay, if you refer to this graph over here, 727, which is somewhere here, degree. This is referring to degree Celsius, and this one is for Fahrenheit. Okay, so 727 somewhere there until 550 around here. So the area around here actually producing a perlite microstructure through hot quenching. Hot quenching meaning the temperature of the solution is controlled to certain temperature so that it would drop drastically. And transformation temperature decrease in this range, the perlite change from coarse to fine structure. Okay, so in this area, the same area. Number 3, rapid quenching. Okay, from rapid quenching 7 to 7, rapid quenching from this point, rapid quenching, it will turn into 100% martensite over here. Later on, you will see the line for 50% martensite and 100% martensite. Okay, so rapid cooling, starting from this point, rapid cooling, reaching martensite. After that, okay, this one 7 to 7 until 550. Okay, so 550. From 550 just now, 550 until 250 at this point, this one austenite can change into martensite. Change into binite. Okay, it's a structure between perlite and martensite. So binite again. If the steel are hot quench from temperature 550 point here until 250 over here, the structure change into binite. So the area is somewhere here. This is binite area. And in binite area, it can be divided into two, which is upper binite and lower binite. For upper binite, the temperature range from 350 until 550, whereas for lower binite, it starts from 250 until 350. And the structure is slightly different between upper binite and lower binite. Okay, so now let's look at the transformation of austenite to perlite through isothermal transformation. And again, this one occur at eutectoid composition, which is equals to 0.76% of carbon. And the process starts from heating the steel or the metal until it reach above austenite temperature, which is more than 723 degrees C. In this case, it is being heated up until it reach 727 degrees C. After that, rapid cooling until temperature 6 to 5 degrees C, and then hold that temperature for a certain duration until it change from austenite into perlite. Okay, again, start cooling. This line represent cooling line, and then until reach point 6 to 5 degrees C. So this is 0.6 to 5 degrees C, and hold that temperature until it reach this one 0% perlite, reaching this line 50% perlite, and reaching this line is 100% perlite. If we want to change the microstructure into only 50% perlite, then the process should stop somewhere here at this line with a dotted line there. From there, finish it, cooling down. You should draw a line moving downward somewhere point here. So basically, you can control the percentage of structure that you want in that material by controlling the temperature and time. Same goes to bainite. Okay, this is how you control the formation of bainite. Firstly, heating up the metal into austenite above austenite temperature, so it will change to austenite. After that, start cooling it. Cooling it. Then reaching temperature of 600 degrees C, maintaining at that point, reach 100% perlite. That one is the same case as above the previous slide just now. And for bainite, start to cooling it up to this temperature, for example, around 490 degrees C, and then hold that temperature until it transforms into 100% bainite over here. And again, this transformation only occur for carbon equals to 0.76%. And the formation of bainite is known as diffusion control. This is the types of bainite that might occur, which is upper bainite and lower bainite, as mentioned to you earlier. This is the microstructure for upper bainite, which form between temperature 350 and 550, and for lower bainite, it occur between temperature 250 to 350 degrees C. And remember, bainite can be formed through hot quenching, so the temperature need to be controlled so that it will not drop drastically. Other than that, the other terminology that or phase that you need to know in iron carbon system is that spheroidite. Spheroidite refers to a microscopic constituent in some steels composed of spherical shaped cementite particles in an alpha ferrite matrix. Spheroidite is the most ductile and softest type of steel on the granular molecule level. Its purpose is to soften higher carbon steels and produce more formability. Okay. Other than that, martensite. So this is as mentioned to you just now. Basically, the slide that I've prepared to you guys actually may have some repetition on how the process on how the microstructure being formed. Okay, so that you may understand it better. So as mentioned to you just now, martensite can be formed through rapid cooling from austenite temperature, rapid cooling, then it will transform into martensite. However, it depends whether 50% martensite, 90% martensite, or 100% martensite. It depends how fast the temperature, how fast that process being cooled, being introduced to that metal, and for how long. Okay, so martensite is a rapid process and it is diffusionless. Okay. And martensite can be divided into two, lathe type and plate type, or combination of lathe and plate type. For lathe type, it can be found if the carbon content less than 0.6% over here. If the percentage of carbon is more than 0.6%, then it will have a plate martensite in it. However, if the percentage of carbon is more than 1%, it will have 100% plate martensite. And this is only the terminology. MS referring to temperature of martensite start to occur. MF referring to temperature of martensite starts to finish. And after transformation, the position of carbon atoms in crystal structure will have no changes, will not change, it will stay there. However, the only difference is that strength and hardness, which will be affected by the carbon content only. Okay, so again, when we look at martensite, this is how it occurs from austenite. Then from austenite, if you expose it to slow cooling, then it will form ferrite and cementite. But if you quench it or fast cooling, you will form a martensite. BCT actually referring to centered tetragonal body-centered tetragonal crystal structure. And afterwards, we are going to learn the tempering. Tempering from martensite, we introduce a tempering process, then it will change back to ferrite, alpha ferrite, and cementite. Martensite is very hard and brittle. And therefore its ductility is reducing or decreasing. And okay, now let's look at the transformation involving non-eutectoid composition. Non-eutectoid. If you still remember just now, eutectic point is where the composition of carbon equals to 0.76%. So beyond that percentage is known as hypereutectoid composition, whereby it has proeutectoid cementite in, or proeutectite is in it, or some people may call it as proeutectoid cementite. And below than that is called as hypoeutectoid. Okay. For phase transformation involving non-eutectoid composition is that the S curve moving to the left. So for this case, it is very impossible for us to quench from austenite region to form martensite phase. So for this case, non-eutectoid is very impossible. That's why we always refer to eutectoid composition only if you want to change the steel into martensite microstructure. Other than that, if we add other alloying element into the material, into the steel, it will change the transition temperature. So it will take some time to reach, for example, martensite or austenite or ferrite, bainite, and so on and so forth. Example of alloying elements includes chromium, nickel, molybdenum, silicon, and mangan. So this process actually, the addition of this element will retard the formation of, for example, from austenite to alpha ferrite and cementite, or bainite or martensite. Now let's look at the continuous cooling transformation diagram. This diagram is used to convert, it's a conversion of isothermal transformation diagram to continuous cooling transformation diagram, or CCT diagram. What is CCT diagram? Well, this one, CCT diagram, is a industrial heat treating operations. In most cases, a steel is not isothermally transformed at temperature above the martensite sub temperature, but continuously cooled from the austenite temperature to room temperature. The number two, the transformation from austenite to pearlite occurs over the range of temperature rather than a single isothermal temperature. As you look at this one, so that's a range temperature. Don't worry, we'll see the example afterwards, more example afterwards. The CCT diagram start and finish lines are shifted to longer times and slightly lower temperature below around 450 degrees C for austenite to transform into bainite. Okay, so this figure shows different cooling rates for eutectoid plain carbon steel cooled continuously from austenite region to room temperature. Curve A is a curve very slow cooling. This is a curve A, such as by shutting off power of an electric furnace and allowing the steel cool as the furnace cool. Microstructure would be cost per light. So this is very slow cooling. By right, the specimen being left in the furnace and it will start to cool together with the furnace. Graph B or profile B here shows represent a rapid cooling. For example, removing austenite steel from furnace and allowing the steel to cool in air. So in this case, fine pearlite will be produced. Okay, I hope you can imagine on how the process being conducted. Okay, imagine you have a furnace, then you place sample in it, steel in it. After it reaches a certain temperature, then you open up the furnace to take out the specimen and put it somewhere for that specimen to cool it down on its own. I mean, in normal temperature, normal air, normal temperature. From there, fine pearlite will be produced. And let's look at line C. Line C producing starts with the formation of pearlite. Line C, okay, line C reaching this point, so pearlite occur in it. But there is insufficient time to complete the austenite to pearlite transformation. The remaining austenite do not transform to pearlite, will transform to martensite at lower temperature 250 degrees C, and therefore for line C, for this case, we will have a combination of pearlite and martensite in it. Okay. Other than that, for curve E over there is cooling at a faster rate. Then this one will produce martensite structure. Same goes to D. Okay, so from austenite temperature, faster cooling, it will produce martensite temperature. However, for E, is represent as critical cooling rate because if the duration or the speed is not fast enough, then it will change to line C, whereby it will produce martensite and perlite in it. So it has to be as fast as possible by referring to this graph, temperature versus time, so that we can control what are the structure that is needed to be produced. Okay, so now let's look at the example on how to determine all those phases, okay, or how to draw, sketch, how to draw a line so that we can produce required structure. Okay, so this example, let's read it together. On the isothermal transformation diagram for 0.45 weight% carbon, iron carbon alloy diagram, sketch and label the temperature path to produce the following microstructures. Number 1, 42% pro-eutectoid ferrite and 58% coarse perlite. B, 50% fine perlite and 50% bainite. C, 100% martensite, and D, 50% martensite and 50% austenite. So let's look at one by one. Question A, 42% pro-eutectoid ferrite and 58 coarse perlite. Well, when you saw a terms pro-eutectoid ferrite, it is actually referring to process before eutectoid with the value of C not equals to 0.45 weight% of carbon from iron carbon phase diagram. The relative amounts of pro-eutectoid alpha and perlite may be determined in a manner similar to that described in previous lecture for primary and eutectic microconstituents. And we use level rule in a conjunction with a tie line that extends from alpha to alpha plus ferrite cementite phase boundary, which is equals to 0.022 weight% of carbon, to eutectoid composition, which is equals to 0.76 weight% of carbon, in as much as perlite is the transformation product of austenite having this composition. So from there, you can calculate it, the weight fraction for perlite and austenite, which is equals to 0.58%, 0.42 weight%. So from there, we know that the material or the specimen can be isothermally treated below than austenite temperature, which is 680 degrees C over here, because we want to produce perlite and coarse perlite and ferrite, pro-eutectoid ferrite. Okay, so cool it over here and hold the temperature until it reaching this point, which is alpha ferrite, pro-eutectoid ferrite and coarse perlite. Now moving to question B, 50% fine perlite and 50% bainite. So this is how you draw. We know that this is the area where we want it to achieve 50% perlite. Oh, sorry, 50% perlite and bainite. Okay, somewhere here. Okay, so isothermally treated, 50 degrees C, somewhere there. So you draw a line there until it reach 590 degrees C, and then hold that temperature until it reach 50% of perlite. So this line represents 50% of perlite. After that, isothermally treated at temperature of 470 degrees C, which is at this point 470 or 490 or 500. Okay, whereby at this and then hold 950 sorry 470 point here. So hold it at that temperature until it reach 100%, not 100%, I mean the remaining austenite form to transform into bainite. So you reach at this point, then cool it down at room temperature. So that's how you draw the line at this TTT graph diagram. After that, 100% matosite. 100% matosite can be only produced from rapid cooling at room temperature, from a austenite temperature, rapid cooling, so straight away from 100% matosite. If you want to form 50% matosite and 50% austenite, which is question D, then still rapid cooling but a bit longer, then until it reach this line, which the temperature around 300 degrees C, then it will start to form 50% matosite and 50% austenite. Okay. Now let's move on to next content, which is hardenability of ferrous alloy. Well, hardenability is a term that is used to describe a given steel's ability to harden, and it doesn't mean what hardness can be achieved from this term. It is usually determined by the Jomini and quench test. In other words, it will show the depth of hardening across an equivalent diameter bar of steel. And the hardenability steels depends primarily on the composition of the steel, austenitic grain size, the structure of the steel before quenching, and the cooling rate. This is how you conduct a Jomini test. You place the specimen over here with this size. The specimen, I mean, after you heat the specimen in furnace, then take it out quickly, as quick as possible, and place it over here and start to spray water to the specimen starting from this end. Okay, after that we can calculate the hardness of the materials, either using Jomini test or Brinell hardness test. For 1080 plain carbon steel, this is a code for plain carbon steel. The hardness value at quench end is 65 Brinell hardness, while it is 50 Brinell hardness at 3/60 inch from quench end. So this is how you calculate the hardness of the steel, starting from point where the material starts to reach start to cool. Okay, because at this point the water will spray at that area first from this point. So cooling start to form this point until at the bottom, at the upper part of that specimen. And alloy steel 4340 has high hardenability and high hardness with the value of 40 Brinell hardness 2 inches from quenched end. This one is another grade of steel alloy. And in alloy steel, the composition of austenite to ferrite is delayed because the cooling rates actually depending on the diameter of the bar, quenching media, and cross section of the specimen itself. That's why the composition or the deformation of transformation of austenite to ferrite is being delayed. These are the data that you can get through Jomini hardenability test. Okay, this is the hardness value through Rockwell's scale, and this one the distance of the specimen. Okay, distance. Okay, other than that, there's a process known as annealing. Annealing is the restoration of cold work or heat-treated alloys to its original properties. While in real life, for example, if you're referring to a human being, after certain duration, after working, after certain training, we might feel stress, we might feel muscle soreness and so on. So to reduce that part, to gain freshness of our body, then we need to go to spa. So after spa, then you'll feel as good as new. Okay, so same things to steel. After certain work or being heat treated, it will feel stress. So to reduce that stress, to gain its original properties, then we will introduce annealing process to it. Okay, three process involved in annealing, which is heating the workpiece to specific range of temperature in furnace, and then holding that temperature for certain period. After that, air furnace cooling. Put it in furnace to slowly cool the temperature. I mean, cooling, let it cool together with the furnace. In annealing, there's so-called full annealing and process annealing. Full annealing, sample is heated sample is heated to 40 degrees C above austenite ferrite boundary, held for necessary time and cooled slowly. Meanwhile, for process annealing, is used for stress relief, applied to hypoeutectoid steel only at eutectoid temperature. And an annealing process is used to increase ductility, to reduce hardness and strength as to modify the microstructure. This is the location of annealing, this side, if you're referring to temperature and carbon percentage over here. Number 4 is normalizing. Normalizing, referring to the process whereby the steel being heated in austenite region and cooled in still air or normal air, and not a blowing air or using fan. No, it's a still air. Some of the purposes for normalizing includes to refine the grain structure, to increase the strength of the steel as compared to annealed steel, to reduce compositional segregation in castings or forgings, and thus provide a more uniform structure, to avoid excessive softness from annealing of steels cooling in still air, and to decrease residual stresses and to improve machine ability. Fine product with small uniform grains, they have higher strength and hardness but lower ductility than full annealing. So you can refer to this diagram for hardness versus carbon content here. Materials that being exposed to normalized process, it will have lower, for this case, high hardness, quenching and okay. Sorry. I'm talking for this case. I'm referring to quench specimen and normalized specimen. So we'll have lower hardness as compared to a quenched specimen. Number 5 is tempering. In this process, martensite steel is heated at temperature below eutectic temperature. This process will make the steel become softer and become much more ductile. Carbon atoms in low carbon steel segregate themselves on tempering. And for tempering, we can see several structure in it, like rod-like or spheroidite kind of like structure. And this structure will form at different temperature. So that's why I said earlier, we need to control the temperature so that it produce a microstructure that is needed by us only. Okay, so that is tempering. And hardness, okay, hardness, it decreases as temperature increase above 200 degrees C. So let's look at this hardness versus temperature over here. So as the temperature increases, the value of hardness decreasing. So you can see the trend from this profile over here. If you compare with 1.2% carbon steel and 0.8 carbon or 0.3 carbon steel, it's all going down, it's all decreasing in hardness when temperature keeps increasing for tempering. Number 6 is mar tempering. The mar tempering or mar quenching process is for plain carbon steel, produces a martensite microstructure and consists of number 1, austenizing the steel. Number 2, quenching the steel in oil or molten salt at a temperature just slightly above the martensite temperature, MS temperature. Holding the steel in quenching medium temperature for a time period sufficient to provide thermal equilibrium of the steel with the medium without causing the initiation of the austenite to braunite transformation. And number 4, cooling the steel at a moderate rate to room temperature. The benefits of mar temperings are to minimize the distortion and crack of the workpiece. Number 2, by subsequent tempering, the mar tempered steel develops a tempered martensite microstructure which provides higher impact energy. Number 7 is aus tempering. In aus tempering, steel is heated. Heated steel is quenched from austenizing temperature rapidly enough to avoid formation of ferrite and pearlite, and then held at certain temperature until isothermal transformation from austenite to bainite is complete, and then cooled at room temperature. Medium of quench is a molten salt cooled in still air. So never use fan or other medium to move the air. So it has to be still air there. Okay. So in aus tempering process, the steel is austenized. Austenized, which is below than 7 to 3 degrees C. Then quenched in a molten salt bath at temperature just above the steel MS temperature. After that, hold it isothermally until the austenite to bainite transform completely this side. At this point, it will transform completely, then cool at room temperature. So that is called aus forming. So now let's move on to our next topic, which is last topic for today, which is mechanical properties. And as mentioned to you in previous lecture as well as in early chapter, the carbon content in steel will affect the properties, mechanical properties of that materials, whereby by increasing carbon content, the tensile strength and yield strength will increase. However, the percentage of elongation will decrease. So it happens both for hypoeutectoid or hypereutectoid. For fine pearlite, coarse pearlite, and spheroidite, the properties also will be different, even though fine pearlite or coarse pearlite might be determined as the same material, which is pearlite. However, the structure is slightly different. So in this structure, in this microstructure, the hardness, the highest hardness goes to fine pearlite, moving to coarse pearlite, and finally spheroidite. And the higher the materials, the ductility of it will decrease. So for this case, fine pearlite will have the lowest ductilities as compared to coarse pearlite and spheroidite. How about pearlite and martensite? Martensite has higher hardness than perlite because martensite is hard and brittle. It is formed through fast cooling. Okay. Tempered martensite. Heat treat martensite to form tempered martensite. Tempered martensite less brittle than martensite. Tempering process reduces internal stresses caused by quenching. So that's why tempered martensite have lower ductility. Lower high ductility. Lower hardness. Sorry. Tempered martensite has lower hardness than martensite. You can refer to this graph over here for yield strength and tensile strength. Martensite is tempered to improve its mechanical properties. Tempering by heating, hardness is reduced and toughness is improved. Heating at temperature of 150 degrees C to 650 degrees C, where it decomposes to two phase consists of BCC ferrite and small particles of cementite. Increasing temperature, tempering time and temperature, hardness decrease due to particles cementite grow bigger. And this graph over here showing a hardness and toughness of annealed steel. Figure A and B showing a hardness, C toughness for anneal plain carbon steel as a function of carbide shape. Carbides is in perlite. Carbides in the perlites are lamellar in shape. You still remember what are the lamellar shape, right? Fine perlite is obtained by increasing the cooling rate. The spheroidite structure has sphere-like carbide particles. And if you notice from this graph, the percentage of perlites begins to decrease after 0.77 weight% of carbon. And this graph showing a mechanical properties of annealed steel as a function of composition and microstructure. If you look at figure A there, graph A shows the increase in hardness and strength. Meanwhile, for B, the decrease showing you a decrease in ductility and toughness with increasing amount of perlites and iron carbide. So in summary, first of all, we need to heat all the material or carbon steel to austenite temperature. Slow cooling will produce perlite. Okay, moderate cooling will produce bainite. Rapid cooling will produce martensite. And reheat the martensite is called tempering is called tempering process, which will produce tempered martensite. And in general, the higher the strength of that microstructure of that specimen, then the ductility of that specimen will decrease. With that, I thank you very much for your kind attention and time. I do hope everybody understand on this topic as well. And if you still do not understand, yes, you may always contact me. It's either through Google Classroom or WhatsApp group. And this is actually the end of chapter 4, which is the end of CO2. So by right next week, we are going to have a quiz for CO2. With that, I thank you very much. Please be prepared and have a nice day. Bye bye.